In this video we're going to look at Snell's law. So let's imagine we had some surface between, say, air and glass, and there's a beam of light hits the glass at a certain angle and it gets bent. So the velocity in this medium here will be v1, and let's say the velocity in this medium here will be v2, and that's the junction between the two mediums. So we can show Snell's law, prove Snell's law using a bit of geometry, so in basic trig. So let's call this distance here A, we'll call that point there A, and the final point over there B, and we'll look at the angle this makes with a perpendicular. So we'll call this angle here alpha 1, and that angle in there alpha 2, and let's call this distance here B, and the distance from here to here we'll call x, and then we'll look at the full distance from this point here to the point over there at B. We'll call that distance C. So this small distance here is going to be C minus the x. Okay, so I'll put a wee note in there, C minus x. Now we're going to use the Fermat's principle of least time. So that's telling us that light is going to travel along a path of the shortest possible time. Okay, so if we use that rule, we'll be able to derive Snell's law. Okay, so what we could say is that we know velocity is equal to distance over time, so therefore we can say time equals distance over velocity. So in this instance, to travel from point A to point B, then we could say that it's going to happen in a time interval. T is going to equal, well, it's going to be this length here. So that length there is a squared plus x squared root. Okay, so we could say a squared plus x squared root, and the velocity is the velocity in that medium, which is v1. Now that's for the first part. Now we're interested in the time it takes to travel from here to here. Well, that's going to be our b squared plus c minus x squared will give us this length here. Okay, so we'll have our b squared plus c minus x squared, that's the root of all that, all upon v2. Okay, so that's the total length of time it's taken, and employing Fermat's principle, which is of least time, which is telling us it travels in a path that takes the least time. So if it's traveling a path that takes the least time, what they're saying is time is minimized. Okay, so if time is a minimum, then if we look to find the rate of change of time with respect to distance, then that should equal 0. Okay, the same as looking at an example, a curve here, and saying we're finding the minimum rate of change, which would be this point here. Okay, it's the same sort of thing. So if we were to then go ahead and differentiate this here with respect to time, then we're going to have, well, for the first part of it, we're going to have half times our a squared plus x squared to the minus a half, and then differentiate what's inside, which is going to be our 2x, and the second part of it, we're going to have our a half of b squared plus c minus x all squared to the power of minus a half, and then if we differentiate what's inside it, we're going to have the minus sign for the x, and we're going to have our value of 2c minus x, and that one's going to be over a value v1, and that's going to be over the value v2. So we can rewrite that then. If we cancel out the 2's and the 2's here, and we take this down to the bottom line and write it in the terms of the root sign. So in the top line we're going to be left with x upon the root of a squared plus x squared, okay, all times our v1 minus c minus x all upon the root of b squared plus c minus x all squared all times v2, and that there is going to equal 0. So we can see then from the geometry that this value x upon the root of a squared plus x squared, well, if that's the angle alpha, then that angle alpha 1, then that angle in there is alpha 1, okay? And so it means that the value x upon a squared plus x squared is that distance upon that distance there, okay? So that's just going to be the sine of this angle here, okay? So that whole thing then can be written as the x upon root of a squared plus x squared can be written as the sine of alpha 1 all upon v1 minus, and the same goes here, c minus x squared divided by this distance here, okay, which is this length here. Now we can write that then as, if this is the angle here is alpha 2, then that's going to be the same as that angle there. That will be our alpha 2. Okay, so that's going to be the sine of alpha 2. So that's just going to be sine of alpha 2 upon v2 equals 0. We'll just take that one across, so you get sine of alpha 1 upon v1 equals the sine of alpha 2 upon v2. So that there is Snell's law. So Snell's law of refraction, I'll write it down there. So Snell's law of refraction, okay, and we derived that using Fermat's principle of least time. Okay, thanks for listening and goodbye.